The assumptions underlying the global computing supply chain, much of it anchored here in Taipei, have shifted to accommodate a new kind of software demand. This chart tracks GitHub pull requests. Growth was steady, 300 million in 2023, 400 million in 2024. But in 2026, output nearly tripled. 30 million developers represent a flat $3 trillion salary base, now generating $9 trillion in productive work. This anomaly exists because the software industry has moved past the limitations of standard generative AI. We are no longer relying on a human to type a single prompt and wait for a single output. Instead, software is now operating autonomously. It is reasoning through complex tasks, evaluating context, and executing multi-step plans without requiring human intervention at every stage. This is Agentic AI. And because it operates continuously, it has forced a complete redesign of the hardware architectures used to run modern data centers. Generative AI's baseline computing pattern is strictly linear. You input a prompt, it runs through the neural network, and produces an output. An agent, however, operates on a continuous cycle, observing, reasoning, acting, and using external tools repeatedly until the objective is met. The tool use node enables the agent to execute deterministic external code. It runs compilers, searches the web, or queries SQL databases to generate exact answers. To keep this loop intact, the system has to maintain a massive working memory, known as KV caching. The agent must constantly retrieve both structured and unstructured data to remember what it just did and what it needs to do next. Because this loop is continuous and highly distributed across different processing layers, mapping it onto standard server hardware creates an immediate, massive latency bottleneck. The exact point of hardware failure occurs during the handoff. Whenever the agent decides to use an external tool, the neural network on the GPU must pass the workload to a CPU. Traditional x86 CPUs were built for human users and cloud economics. They are optimized to slice up cores and maximize multi-tenant throughput. They were never built for the nanosecond interactivity demanded by autonomous software. While the traditional CPU takes its time executing deterministic code, the highly expensive neural network on the GPU completely stalls, sitting idle. This bottleneck required a custom hardware solution. The Vera CPU is an entirely new architecture designed exclusively to minimize agentic latency and accelerate Python sandboxing. This cross-section of the Vera Olympus core shows its 10-wide decode engine, executing 10 instructions per cycle for peak single-threaded performance. Integrating LPDDR5X memory directly delivers 1.2 terabytes per second of bandwidth, slashing peak latency by 40% compared to x86. Furthermore, all 88 Olympus cores are unified on a single monolithic mesh. With no chiplet boundaries to cross, the cores communicate at a cross-sectional bandwidth of 3.6 terabytes per second, hitting the physical limits of the reticle. In high-stakes, data-dense environments, like real-time stream processing for the New York Stock Exchange, this architecture processes telemetry 6 times faster than previous generations. The CPU functions as the latency-critical conductor, orchestrating the flow of data for an impatient AI. Achieving this level of interactivity requires manufacturing precision that scales from the silicon die to the entire rack. The Vera Rubin system maps the software loop directly into physical space. If the GPU is the brain handling the neural network, the CPU rack acts as the workshop, managing the tools and memory. This server rack relies on a physical breakthrough, a solid central PCB midplane. This single component replaces the thousands of individual copper cables that previously routed data between trays. Removing those cables drastically increases the mean time between interrupts. It also slashes physical assembly time. What used to take 2 hours to rack and cable now takes just 5 minutes. Sitting directly on the critical path of the system are the Vera Bluefield 4 STX accelerators. They handle the massive storage processing required to manage the agent's KV cache without interrupting the flow of compute. At this pod scale, the hardware functions as a monolithic disaggregated system designed for extreme efficiency. Scaling these pods up to the factory level reveals the hardest physical constraint of modern infrastructure. An AI factory costing $100 billion is strictly limited by its fixed 1 gigawatt power grid budget. Because an installed gigawatt is a hard ceiling, the ultimate economic metric for these facilities is tokens per watt. Every token generated is a unit of revenue. Therefore, power efficiency directly equals profitability. Agentic workloads burst dynamically, thinking quietly for a moment before suddenly executing a massive tool call. This leaves some racks idle, while others max out their power draw, creating inefficient, stranded watts. To recover that stranded power, the DSX Max LPS system coordinates with teams of AI agents, actively steering power across the facility. It routes wattage away from the cool, quiet racks and sends it directly to where the heavy workloads are happening. This dynamic power smoothing flattens peak current spikes, allowing operators to safely over-provision their GPU capacity by up to 40%, while remaining strictly within the exact same grid envelope. The entire data center has effectively become a single computer, and its absolute performance limit is dictated entirely by thermodynamics. As the hardware infrastructure adapts to handle autonomous workloads, the foundational software models are evolving to capitalize on this exact efficiency. The Neutron 3 Ultra model moves away from standard designs, utilizing a hybrid architecture that combines a state-space model with a mixture of experts. By processing data through this hybrid structure, the model achieves a 5-fold increase in speed, while simultaneously lowering total inference costs by 30%. The mixture of experts design is what drives this cost reduction. Instead of brute forcing every calculation through the entire network, it selectively activates only the specific neural pathways needed for a given task, drastically reducing the overall computational waste. When the underlying architecture is this efficient, models can afford to think longer for the exact same cost, rapidly expanding their ability to operate autonomously. This agentic loop is now extending beyond digital data processing, expanding into systems that must navigate the unpredictable physical world. The Cosmos 3 architecture was built for physical AI. It uses autoregressive and diffusion transformers to process action, sound, and visual data from a first-person robotic perspective. But teaching a robot creates a severe data bottleneck. Unlike language models, which learn from billions of scraped internet documents, you cannot scrape physical, real-world training data at scale. The solution is to use massive compute power as a synthetic data generator. Through platforms like Isaac Root, AI factories simulate accurate, physics-based environments, generating the exact training data robots need to understand reality. By closing this continuous loop, physical AI can now accurately translate digital reasoning into high-precision mechanical motion in the real world. From the reticle limits of a single CPU core to the power grid of a gigawatt factory, hardware and software now function as a single engine built for autonomous agents.